Hello, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. The topic which we are covering and continuing is the divide and conquer approach. I call it an approach because it is not an algorithm which works for every problem. Okay, so this approach we covering the background, and in the part A we covered the basics. So there is the supplemental website which is ezmcq.com/goget. So this is the table of contents or the contents covered in this course, and we are at the topic number 4, which is divide and conquer algorithms. So a very brief overview of the learning management system which is used for execution of this course. And as you can see, there are quite a few very powerful features. Actually, you can run the course as per your level of liking, difficult or medium or standard or easy, whatever suits you. You can also change the interface as per your liking, color, fonts, line spacing, and so on. Of course, you can test yourself also with the end of topic MCQs, which are graded and the results are analyzed. So now we move on to the course itself. Okay, so there's the supplemental website. And as you can see, there are core computer science courses along with cutting edge courses such as natural language processing, artificial intelligence, machine learning, and so on. So let's move to the course of our interest and then to the topic of our interest. So we move to the course of our interest, and the topic of our interest is divide and conquer algorithms. So we move on there. And the first 5 Q&A were covered in lecture 4A. So now we move on to the next set of questions and answers, which is 4B, which we are covering right now. So how recurrence is used to solve problems using the divide and conquer approach. So that recurrence basically will be explained to you with these examples. And these examples basically will help you get the necessary background of the divide and conquer technique. So this divide and conquer is based upon the recurrence relations, okay, which we have covered in topic number 3. And recurrences are used to express the time complexity of the algorithm and also the space complexity of the algorithm. Not directly the space complexity, but it does work directly for the time complexity. So let's take a look at this example of the merge sort. So what we do in merge sort is that we divide the problem into roughly two subproblems of equal size, and then there is the effort of merging these results when the base case is reached. So dividing the problem into two problems n by 2, and these are two problems, plus this is the merging effort, which is linear in time. Of course, this starts with the merging of results of total size 2, then total size 4, and so on. So overall time taken is linear. So from the Master's theorem, the time complexity comes to be order n log of n. Now with the quicksort, we don't divide into two equal parts, okay? So this division is based upon the random location of the pivot key. So that divides into k, one partition is size of k, then there's the size partition of n minus k minus 1, and then the pivot itself. And then is basically it's not the merging, it is the order n over here is moving the keys as per the pivot, which we will be covered in the example part of this course. So the time complexity on average is order n log n, but in worst case, this can result into order n square. Then is the binary search. So in binary search, if you look carefully here, this is basically n over 2. This is a type of n over 2. So we are basically dividing it into half, but we are throwing away the second half. So there is no 2 here. So that is why the time complexity is order log n as per the Master's theorem. And then of course is the fast matrix multiplication, Stressen's matrix multiplication. So these say for example these numbers are to be multiplied, and this is these two matrices have to be multiplied, and this is the answer, and this is the way it is, and this is how this is divided into smaller matrices of size 2, okay, and you can see that there are 7 such divisions. So from the Master's theorem, the complexity is order n 2 power 8.1, which of course is better than order n cube. So if you are interested more than these other references, okay, so let's move on. So how Master's theorem is used for the analysis of divide and conquer algorithms. So prior to I gave you the background as per the certain cases, certain applications. So this is the Master's theorem, okay. So A is the number of subproblems and B is the factor by which the problem size is divided. So in binary search, A is 1. Binary search A is 1 and B is 2. And for merge sort, A is 2 and B is also 2. And D is 1, okay. And for, so this is how the Master's theorem works. So we look at these three cases, the details are here. So let's consider the case of when A is greater than B to the power of D. So when D is 1, and then we get, this is the time complexity that we get. So it is fairly straightforward, the background to understand this. Okay, so how do we, so we looked at the master's theorem. Now we do the actual apply the master's theorem, how we can apply it. Okay, so how we do it, first of all, what are the perform without using master's theorem. So this is different. So instead of using the master's theorem, now we do the complexity analysis without using the master's theorem. So basically we will be getting more depth and detail. So what are the techniques? So express the recurrence as we did in the master's theorem. So the recurrence is expressed the way it is. There's no changing in it. And then we draw the recursion tree. Then we draw the corresponding tree corresponding to that recursion and calculate the work done at each level, because there are certain levels of that binary tree. There's certain height of that binary tree. Okay, and and of course there it may or may not be a binary tree. It's a recursion tree. And calculate the work done at each level of the tree and sum the work, which is the total work done across all the levels. Okay, so let's look at the example of merge sort. So using the recursion method, this is the way we write the time complexity. So it has nothing to do with the master's theorem. This is the way we write it. Okay, and order n is the time complexity of merging the results. So draw the recursion tree. Okay, so if you look at the example here, so since we are dividing into two parts, so this is divided by 2. Of course, if we divide into 7 parts, then it's n by 7. Okay, so that's why I said it may not be a binary tree. So if you look at this, so when we keep on dividing it, right, and we reach n leaves, then the height of this binary tree is log of n. Height of the binary tree is log of n, and the effort or the work done at each location is n, right? Is n. So n by 2, n by 2 total is n. N by 4, 4 times is n. So that overall time complexity is order n log n. So that's not very difficult to understand. Okay, so what are the applications of divide and conquer algorithm? So there are many applications, merge sort and quick sort, which we will be covering in this topic. Okay, then is the matrix multiplication, Stresson's method, which I briefly mentioned in the previous Q&A. Binary search, closest pair of points, will go into a lot of details, how this works and how it's better than the brute force approach. And then finding the strongly connected components, I'll explain it to you, but more coverage will be in the graph algorithms, not in this divide and conquer approach. So in merge sort, it's the classical example of divide and conquer, divide into two halves and keep on dividing it and then merging it. So that takes order n log n time. Quick sort, it's the pivot, and even if the pivot is wrong by 90%, even then the time complexity is n log n. Matrix multiplication is the Stresson's method into smaller sub matrices recursively, okay, and then multiplies them. So the time complexity is as per Master's theorem, n log to the base 7, 2. That comes to about n power 2.81. Binary search is log of n, right? We are performing searching, that's it, binary search for a sorted data set. And of course, closest pair of points using a brute force approach is order n square, which is a trivial approach, but n log n is better. I will explain this to you. And the graph algorithms are strongly connected components and the maximum subarray. So what is a strongly connected component for a directed graph? Is that in a component, every vertex is reachable. So this is a strongly connected component, and every vertex is reachable. That is another a strongly connected component, okay? Because every vertex is reachable. This is another. So there are 3 strongly connected components which can be discovered using the divide and conquer approach. More applications of divide and conquer approach is this we have mentioned already, closest pair in 2D or 3D, and polynomial multiplication, and of course convex hull. Convex hull is the hull which covers the points such that if you draw a line, the line does not goes out of the hull. And then is the dynamic programming. So we have a whole topic on dynamic programming where we use memoization, and there are overlapping sub problems, and we store the sub solutions and load them and use them subsequently, which results in reduction of the computation time and bookkeeping also. And image processing, quad tree is very interesting, used for compression. So what happens in a quad tree is that you divide the space into 4 parts, okay, and within the parts you have that data point, and this is used for JPEG image compression and image analysis. So these are, say for example, are the 5 points. So if we divide it recursively, so this is one division, this is the second division, and so on, till we have a point within a quadrant, or a quad. So this is how it's represented as a quad tree. So now let's move on to more interesting Q&A. So before we move on to more interesting Q&A, let me show you about the quad tree which I was mentioning. So you see that we divide this into 4 parts like this, okay. Then we divide it into 4 parts like this, okay, and then we further divide it into 4 parts like this, okay. So these are different levels, and this is how the C goes to this point, and E goes to over here. This is the first level. This is say quad 1. This is the second level, quad 2. This is the third level, quad 3. And this is the fourth level, quad 4. So this is how it works. I hope this helps you understand the concept better.